So you take a pile of powder, make a final component, how to control the flow properties so that you create the shape, you remove the polymer and you sinter the particles, and you come to the final shape. The aspect of polymer removal and sintering we will look in the classes tomorrow, right? But basically we will look at how to categorize a whole bunch of ways to create shapes with powders, right? So one way of looking at powder processes, just like we said, was how much pressure is required, and that depends largely on the binder content. In the case of die pressing, so solid additives, right? You add very little of this, and you have to use a lot of pressure to compact that into a shape. In the other extreme, we might use, for instance, your coating process, right? You make a suspension of particles and you coat the foam with it, right? And so you have, relatively speaking, a lot of binder, right? And you can do it at atmospheric pressure. You don't need a whole lot of deformation pressure to create that type of a shape, right? And then in between, there are a whole bunch of possibilities, right? Depending upon how much binder you might have. Of course, addition to that is what physical state that binder is, right? Let us start looking at some processes where you have solid additives or lubricants, or you might in some cases have no additive at all, right? And so these are some kinds of processes that are available. We'll start looking in detail, some detail with die pressing, and look at two small variants or three related to die pressing. Then we'll take one more fourth variant of the same die pressing case where you begin to now get rid of all additives altogether. And finally, we'll use a laser beam to sinter particles. Okay. So that's going to be one type of agenda. Okay. So what you do is you take some powder, so you blend it with a solid additive, zinc stearate, ethylene bisteramide, those are some possibilities, and you blend them together, right? In some cases, as in the case of making some kinds of ferrous materials, you might blend the iron powder with some graphite powder. Maybe you might add some nickel to it, things like that, to change the properties of the final mixture. And then you pour the powder into a die, which is basically a hole. There can be two punches, one at the top and one at the bottom. You can apply pressure just from the top, or you can apply from both directions. You squish the powder together. This top punch rises, and then the bottom punch pushes the part out of the die, and then you get a pellet like that. You can now take that shape and sinter the material separately. So those are three major stages. So the kind of parts that you might create with something like that are all these kinds of complexities. Okay, so you might see in some cases it's a very simple part like a gear, right? So the nature of that die would be such that you would have one punch through the middle and you have one punch through the bottom, and then you can basically end up creating shapes like that. What are some common attributes of these shapes that you can think of when you see some of these different shapes? There's something common about all of them. Can you visualize? Pardon? Okay, they have some kind of a circular symmetry to it. Something else, very good. Something else that you can observe? Yeah, they can be metallic, but they can be ceramic as well. Yeah, but just a shape. Smooth surface, yes. But what about the axis of symmetry? Yes, not all of them, right? So you can create, you can have a few different. They fall into certain regions. One can be a simple shape like this, maybe with a hole, maybe not with a hole. So it could be just a cylindrical pellet, or it could be a pellet with a hole through that, you know. So that could be one type of a variation. The outer geometry itself can have some teeth as for gears, and that could be a variation over there itself. But the gear, the basic gear, can have two levels, and it can have an internal feature. And so at that point, you're beginning to look at something like that. Okay. That would be another one where you have now two different cross sections, and that looks like that, something like that. Okay. So mainly you can have either a single level or you can have different levels. The Depending upon the number of levels you have in the part, you can have multiple punches and they can all be controlled independently of each other, right? But mainly you're providing as high a pressure as possible and you're pushing a part out. The other thing common to many of these parts is the fact that if you push powder into the die and then you clamp it with a punch and you take the punch off, you need to be able to push the part out. So if there is something like a side hole that is coming in, or if there is a lip like this, then you will not be able to push the part out. It will get locked in. This is different from injection molding where you can open the mold from and be able to remove a part. Here also undercuts are important, but then you can have multiple motions to remove, to open the mold. And so side holes, so if you're pressing the part like that, you cannot have a hole in this direction unless you have an independent motion. And you cannot have this type of a way, because if you push this, it will get locked in place in the die over there and the part will break. Right? So mainly what you have is you start out with loose powder, apparent density, right? And you begin to increase the compaction pressure, and slowly the compacted density increases. It does not, initially the density increases rapidly, and then after that, for an from 0 to 20, your density is almost doubled, but then to go from 20 to 40, you almost have just a 10% change, right? So as the particles come closer together, there's more friction, and so the extra pressure that you might need to get over that, to overcome that, right, allows for a lot of dissipation of energy, right? So you're reaching the limits of mechanical deformation of the powder and based on the material characteristics. So for iron powders or some aluminum powders or something like that, you will be able to go through a much steeper curve compared to a ceramic material where you will not, it will flatten out much faster because the material is a lot harder. And okay, so basically green, yes. You can, well, if it's a metal powder, you can deform the particle, but otherwise all you're doing is trying to push the particle closer and closer together and eliminate some of the porosity, right? So if you have agglomerated ceramic particles that are, you might be able to break up some of the agglomerates as you're pushing it together because they are weaker and it'll rearrange. But once you reach a certain level, then there's not much deformation you can do to get rid of the space. If you have a wide enough distribution, you might be able to push some particles into spaces to pack better, but there's a limit you can do it. But mainly, density increases as pressure increases, but each material is going to have a different behavior. Okay. So now this, so now you press the material, you got to push it out, and so there is going to be a frictional force between the part and the die wall as you push the material out, right? And so that is useful to characterize because that determines, first of all, your throughput, and it also then determines the lifetime of the die cavity itself, right? So this is the ejection stress. As you're pushing the part out, what is the friction, what is the stress required to overcome the friction between the part surface and the powder surface? You can imagine the more complex the external geometry of the part, the higher the surface area, the greater the stress is going to be. But this is now for parts. Aspect ratio means how tall is it relative to the diameter. Okay, so that's aspect ratio, and these are two different compaction pressures, right? We went back to here, one pressure here, one pressure there, right? So different densities. What are some things that you see in this plot? Yes, the more dense the component, the more difficult it is for it to eject, the higher the ejection stress is. So there is a trade-off between getting a high enough density and wearing out your tool faster, right? That's good. What else can you see? Right. So if you have an organic additive to lubricate that, the ejection stresses are lower, the friction between the particles are reduced, and the friction between the part and the wall surface is reduced, and so that is beneficial. And then finally, the higher the aspect ratio, so taller parts, right, have a higher surface area and are going to require more ejection stress. Right. So main thing is depending upon the material composition, right, whether you lubricate it or not, depending upon the geometry, okay, and depending upon the process, there are some parameters that are changing. So we talked about material, process, geometry, interactions, right? They are all related to each other in some manner, and some responses related to the process, some response related to the properties of the component, all change. So that is what I would like to illustrate with this, right? And we'll continue to build off that theme. Another thing that happens is the density is not very uniform. Even a simple shape like this, right? Cylinder, if you take a cross section of that, and if these two are the pressing directions, you will notice that in the core there's a little bit higher density, and near the corners there are a little bit higher density, but over here the density is lower. So you just pressed it from the top, okay? And you can see, right? So density is not uniform. We talked about homogeneity a lot in the last class. What happens if the density is not uniform to start out with? What happens if you're going to center it? Some regions are going to densify faster, I mean, differently compared to others. And so you will have porosity somewhere, you will have higher density somewhere. Mechanical properties are going to change. This has less powder, so to get the same final density, it has to shrink more. What is going to happen to the dimensions in this region compared to the dimensions over there? Right? Going to change. What about internal stresses? One part of the region of the part wants to go one way, the other region wants to go another way. So you have internal stresses created, and you can have premature failure. So gives you an idea that this has to be controlled to some extent. And so what happens in practice is components that are made in this manner are never really sintered to the full density. They are only sintered to a fraction, to a part of a density. You will go from 60% dense when it's pressed to about 90% dense, and you'll have very minimal shrinkage, maybe less than 1% or so, because you cannot afford, you're unable to have that type of large shrinkage in all directions, 15 to 20%, as we will see in the case of melt processing with injection molding, where it can be a lot more uniform if you do it correctly, right? So one thing is homogeneity, right? Even here in a simple case can be very different, and it has to do with the fact that, right, the pressure transmission, because of friction, it's going to lose, there's going to be a loss of pressure as you go down to the depth of the material, and as you go from the wall to the center, right? There are going to be frictional losses, and so there's going to be less pressure that you transmit available in certain regions, and so that means lower density, right? So we see that density is a problem, and so one way to deal with it is, instead of having pressure in only one direction, to have it in all directions. So hydrostatic pressure as opposed to what is called uniaxial, one axis pressure, which we see over here only in this direction. We try to have it in all directions. And that is possible by either with the application of heat or without the application of heat, right? So isostatic pressing, you can have temperature, you may not have temperature, additional temperature. But what you typically do is, now you can make some simple shapes, perhaps, where you put the pack the powder into a rubber mold, okay, which is thin walled, and you put it into a chamber which is surrounded by a liquid, and you increase the pressure on the liquid. So now you have uniform pressure from all sides, and you can deal with removing the density gradients. Okay. But now it has become more complex. Here, you put powder in, you put the punches, take out the punches, push the part out. It's relatively a rapid process. Okay, whereas now you had to fill it into a bag, put it into a liquid, close the liquid, apply pressure, take it out, remove the stuff out, right? So there's a penalty, right? Now, if you're making a few components that require a very high strength or hardness or high temperature resistance, right, all affected by density, then you can go to something like that. But as the volume of manufacturing increases, the ability to use this type of an approach goes down. You can alternatively fill the powder in a deformable material such as a tin box, or you can even make it into a very thin walled steel material depending upon the temperature you're heating it. Okay. And then you can assemble all those parts in a huge chamber, fill it up with a gas, heat it, and pressurize that whole chamber with gas. And now you will have isostatic pressure from all directions, and you can heat it as well. In doing that, you can sinter the part under pressure, and you can get very high densities. So you don't have to take out the component and sinter it separately. You sinter the whole material under pressure. So turbine rotors, automobile connecting rods, right? Some hip prosthesis, turbine blades, all can be made, right? All requiring high demanding applications which require full density, right? Because we saw that over here, because of the density gradients, we will not be able to achieve full density without having warpage of the component, right? So here, because you can remove all the porosity and you're compacting it under and sintering it under pressure, you can eliminate porosity completely, and these types of applications will need that type of full density. And you can do it by isostatic pressing under heat, so-called hot isostatic pressing, as opposed to cold isostatic pressing, which is done at room temperature. So same thing, take some powder, apply some pressure. Depending upon the direction in which you apply the pressure and whether you apply heat or not, you have some variations in the type of component that's created. In hot pressing, instead of iso, so it kind of tries to build the combination of advantages. This is very expensive because you need to have a safe pressurized chamber that can fill in parts. And so that is going to obviously require high safety, because have you ever seen an exploding reaction vessel? You had an explosion, you said, in your lab. Maybe not too many. Huh? So imagine that a room of this size or half the size under pressure, very high pressure, right? And something goes wrong, right? It can be bad. So one way is you try to get some combination where you can press the part in one axis as before, but you also heat the die at the same time, and so you can sinter the component. What are some advantages that you can see to being able to do something like this, as opposed to pressing the part and then sintering it separately? Heating the part as you apply pressure. So apply temperature and pressure at the same time, as opposed to sequentially. Conceptually, what is changing in the material property that allows for some benefit, some process benefit? What happens to mechanical properties as you raise the temperature? Okay, so material, because right, it's same as blacksmith heating a piece of iron and then hitting it with a hammer, right? As opposed to just hitting it cold. Deformation can happen at higher temperatures more easily than at lower temperatures, and you can get higher densities. No, you're here. You're well. Even in forming operations, right? You are not near the melt temperature. You might be somewhere between less 40% of the melt temperature to 60% of the melt temperature. So it just glows as red hot, but it is still about only two-thirds of the way at best to the melting point, right? But it has become soft enough that you can squish it. What happens is, in addition, of course, you increase diffusion of atoms, and so you might get more strength in the component by the time you're done. In this case, you get to a high enough temperature, sometimes typically close enough to the sintering temperature. And so in addition to compacting it better, you're also sintering it under pressure to make, and there are some materials that just don't sinter well at atmospheric pressure or in vacuum. It needs additional pressure to be able to force diffusion of atoms. Main thing is press it one direction, you press it in many directions, you heat it, you don't heat it, and you got different ways to create components, and accordingly you can get either low density products or high density products, more uniform density products or not. Okay, when you're trying to heat this material, the typical heating methods are quite slow, and so the heating rate is low, and so your throughput is going to be a lot lower.